I will present a proposal for experimental methodology to carry out tensile tests of superelastic wire and some application of nickel titanium thin wire. Just a brief outline of my presentation, some brief introductions, a proposal of a tensile test for superelastic warp cycling, some fatigue test we carry out, the results, with discussion and concluding remarks. Shows some data of the superelastic nickel titanium wire we use, 5.5 mm in diameter, with ultrafine grain microstructure. The surface condition was black oxide, and the obstinate phase was stable at all the temperature would be used for test. So we are in this situation. Just to remember the difference between functional and structural fatigue. The structural fatigue takes place mainly the first 100 cycles, so that they continue a little, but it produces a dip. The first 100 cycles of dip reduced in the transformation stresses, and the structural fatigue takes place later, mainly is related with intrinsic resistance of the material. This is important for our proposal, the difference. Usually there is a lack of information in the literature about mainly the tensile test experiments. There are maybe some results by using rotary bending or roto bending, but test by using simple devices like this one. Different groups use these devices. They apply some geometrical setting to apply a given strain. Here we have another one. But the problem is all of them apply very complex stress state distributions, inhomogeneous transformation front, and also a high speed are applied, rotating speed. So the idea is to look for a better procedure to analyze the intrinsic behavior of the material, to try to develop a tensile test for superelastic, so for cycling. And this, when we're dealing with thin wires in tension, we need to use this kind of device because we cannot get a geometric dot bone shape specimen, mainly when we want to analyze also the surface condition of the wire. But we have an extra problem with this kind of material, the transformation, martensite transformations, usually take place in the clamp. So the idea was to propose, in this case, we call a virtual dot bone specimen. We take advantage of the functional fatigue to localize an effective zone on of the wire with functional fatigue. So the idea is to apply a near isothermal cycling, a very low stroke rate. So we are sure that we have isothermal situation and the transformation initiate in this place. So here we have schematically this is the procedure. We have the elastic loading, so later the peak stress to nucleate the transformation domain, usually in the clamp. Later as we apply the strain to the maximum strain, we have the transformation, and the transformation front moves to a given position along the wire. Sorry. So we have the unloading, elastic, and later the retransformation. So by cycling between these two strains, we have functional fatigue localized in this region between these minimum and maximum positions. So after applying 100 cycles at very low strain rate, we can localize that functional fatigue. So after 100 cycles, we have lower transformation stresses in this region. So after unloading, we have these situations. We have this region, the effective length with functional fatigue, with lower transformation stresses, and the rest with only this part is only one cycle. So later we are ready to apply the fatigue test. So later we can improve or increase the strain rate, maybe 1 order of magnitude or something like that. We are to continue checking this point. Just to be sure, we can apply one cycle with the same strain range. So the transformation domain nucleate without regions and proceed cycling. We can continue cycling in this region. So we can see here it's also a very good picture. I'm working on that. We have the two transformation here and the maximum deformation, applied deformation. So this is the real data of stress strain. This graph is related with the creating of PDB specimen, and this one for the fatigue test itself. So here the experimental data, we carry out this experiment at 3 different temperatures, different strain range, and here we have the results. Almost all the case, the number of cycles to fracture was around 10,000 cycles. For comparison purposes, we carry out also fatigue tests without transformations for austenite phase and Barton phase here. Here are the results. You can see this is a reference also for titanium alloy on this reference. We can see clearly that the austenite phase without cyclic plug transformation, we have 2 orders of magnitude fatigue lines, 2 orders of magnitude higher. But the important thing here for elastic cycling, we have a fatigue life that does not depend on the applied strain range nor on the mean strength. It seems to be independent of the test temperature, at least in this range. So it seems to depend mainly of the number of transformation experienced by the wire in this region. So in all cases, the fracture took place in the free length of the effective length of the wire with functional fatigue. So just 2 more things. Just remember, the effective strain rate is quite important. In this case, is our results. Here's some equivalent strain rates from some results from Warner and Sawauchi literature. This one is 2 orders of magnitude of our test. But it's clear it's an effect of the strain rate due to thermal effects. We should remember also that in some case when using Bastian confirmation equations, this was proposed to analyze elastoplastic behavior. So here we have some localized deformation and superelastic damage. So include new test method for characterizing new action, pull fatigue life of superelastic wires we propose. We call virtual bond because it's like a virtual bond was not give, we don't change the geometry, we localize the damage there. We carry out some pseudoelastic fatigue tests, and the results mainly show that at very low strengths, on isothermal conditions, it depends basically on the number of cycles of transformation, So it seems not to depend of the strain range or strain mean strain. So of course we have to continue later, because this kind of experiments are long. It takes 1 month, so we want to reduce the time to generate the specimen and to carry out the test. I think that now we can look for, at least it allows us to analyze the influence of intrinsic parameters and the fatigue damage of the material. Thank you for your attention.